Hello, I'd like to tell you about our work in discovering multiple algorithm configurations. Consider this video of Atlas from Boston Dynamics performing a series of actions. How many algorithms does a robot like this have? It may have methods for controls, stay estimation, sensing, grasp planning, collision avoidance, footstep planning, and many others. Our work is about how sophisticated algorithms can be configured so they work better in multiple environments. Many algorithms are highly parameterized. Consider a recent visual inertial odometry method, DNVIO. While it performs very well, its performance can depend on the 35 floating point parameters and a dozen integer parameters that control its behavior, and this is typical of many methods used in robotics. How are these algorithms typically configured? In practice, developers typically pick parameters themselves based on small isolated experiments or intuition of systems designers, but if we have more time, we can do a little bit better. We can gather a dataset of examples around which we can construct an evaluation metric. This gives us an evaluation function that takes in a configuration vector z and produces a scalar cost c, which aggregates the cost of the algorithm across the entire dataset. Once we have an evaluation function, we can repeatedly call it from a black box optimizer and get an optimized vector z-opt. Black box optimization methods can optimize functions without access to the gradients. These typically include Bayesian optimization and evolutionary strategies. In this work, we propose that it's possible to partition a dataset during optimization. This partitioning of data happens based just on the response of the chosen algorithm to different configurations produced by the optimizer. This produces multiple configurations, each corresponding to a disjoint set of data, and a label vector that assigns each data point a configuration. Our hypothesis is that many algorithms prefer different configurations in different, easily detected environments. For example, perhaps there are different configurations for indoors or outdoors, or textured scenes versus textureless scenes, perhaps planning environments that require deep search versus ones that prefer wide ones. To perform the partitioning operation, we consider three strategies for when to assign different labels to the data. The first is a post-hoc strategy, where black box optimization is used to do exploration, and partitioning only happens after the optimization is run. The second is a stage strategy, where half the function evaluations are used to do exploration, then the dataset is partitioned, and then we run separate optimization runs on the new disjoint data. And lastly is an online strategy, where we initialize a multi-arm bandit for each data point and pull handles to decide which optimizer it's going to be assigned to that iteration. In all of our experiments, we only use two clusters to show you the value of even minimal partitioning. To perform partitioning, we set up an objective function for optimal splitting. This takes the form of a linear program that minimizes total cost. Here, Cij is the cost for data I and configuration j. We require that each variable 0 or 1, and that all data points have exactly one configuration assigned to it. We also require this chosen number of configurations to be greater than or equal to k. Given k, it's also possible to evaluate all m choose k sets and return the best, and that typically ends up being faster when k is equal to 2. For our main example, we'll look at stereoscopic depth matching, which is used to produce depth from calibrated image pairs. We'll use OpenCV's semi-global block matching method as an example and tune its parameters, which include regularization strength and outlier removal. We created a dataset by combining two Middlebury datasets and did an even split, getting 23 training images and 24 test images. You can see an example clustering produced by our method below. In general, we found that the images in cluster 2, with the blue outline, had large textureless regions that were more dominant. To perform evaluation on the test set, we use one nearest neighbor lookups based on image embeddings. In general, one could use any supervised method, but with our small dataset and even to train and test split, we felt that nearest neighbors was a good choice. You can see an example of how test images were classified below. Many of the blue outline images do seem to contain large textureless areas, much like they did in the training set. The nearest neighbor classifier only chose the best configuration about 2/3 of the time, but that was enough to capture about 3/4 of the performance gap between the better and the worst configurations, meaning many of the classification errors were on images with small differences between the two configurations. For a qualitative example, here's a qualitative example of matching results. You can see in this image, the second configuration is worse, specifically in this chosen area. For this other image, the opposite is true. The first configuration ends up performing worse and having more artifacts. Both these test images are correctly mapped to the better configuration with our simple classifier. Overall, our combination of partitioning the dataset and picking a test time configuration with a classifier ends up performing better than optimizing a single configuration. Both the post-hoc and stage strategies produce a clear improvement in performance. The online approach is less reliable and only sometimes finds a viable improved split. We also show the benefits of our approach on a commercial depth sensor, the RealSense D435. In this case, we generate 500 configurations and evaluate them all on real scenes. This is a form of optimization using random search and our post-hoc method. We build a pseudo ground truth using temporal accumulation while painting the scene with an infrared pattern projector and evaluate against that configuration. Once again, we find two configurations with improved performance. The first is a configuration that works better outdoors, as you can see here, while the second configuration works better on these large, flat indoor surfaces. While the stereo experiments focus solely on performance, some methods require balancing runtime and performance. In these cases, we optimize the geometric mean of runtime and performance. In the first example, we can optimize sampling-based planning algorithms like informed ROT star. We typically find that we discover one configuration for clean scenes where goal heuristics are effective, and another for noisy environments that require wider search. And lastly, we show performance optimizing a recent visual inertial odometry method. We evaluated 5 scenes, each taken from a different environment in the TUM-VIO dataset. While we expect our optimization to perhaps separate the indoor and outdoor sequences, instead optimization found an alternative configuration for the slide sequence. The slide sequence is unique in that it features very high-speed motion in a very difficult tracking environment. In the slide sequence, the camera goes up a set of stairs and then rides down a large enclosed slide. This is a very difficult tracking environment, as much for the speed as for the lack of features. For this sequence, our method finds an alternative configuration which uses more features and optimization steps compared to the configuration found for the other 4 sequences, which prioritize fewer features to get better runtime performance. And with that, we'd like to thank you for listening to this talk. Hopefully you found this work interesting and you find value in discovering a portfolio of configurations for the algorithms that you use and develop in your research. There are more details and experiments in our paper, and the code is available on GitHub. Thank you.